Hello, everyone, and welcome to my talk, Game of Cross-Catch. Let's win it in a more effective way. And in this presentation, I will talk about how to solve challenges in cross-catch attack and perform cross-catch attack more efficiently. And my name is Le Wu. You can follow me on Twitter. And I am the author of Dirty Pagetable. And in this talk, I will use Dirty Pagetable again to exploit a NPU bug on Samsung device. And here is the agenda of the talk. I will briefly introduce the cross-catch attack, followed by highlighting two challenges in it. Next, I will delve into the most important part of this presentation, using a specific vulnerability as an example to analyze how to address the two challenges in cross-catch attack. Then I will demonstrate how to exploit the file UAF with the Dirty Pagetable on Samsung device. Finally, I will make a summary. First of all, let's take a look at the cross-catch attack. Here is a simple example of UAF. We can trigger the UAF to get the victim object A, and then we can reclaim the victim slab to page allocator. After that, we can let keymap catch B reuse the pages of victim slab. By doing this, we can make victim object A to be reallocated as object B. Now, if we perform operations on victim object A, we will corrupt object B. Following this, we can make use of corrupted object B to get a root. This is a simplified process for cross-catch attack. In a more general context, object A or object B can also be pages or other types of memory regions. As we can see that cross-catch attack is getting really popular. There are a few reasons. First, original vulnerable object is not exploitable sometimes, so we have to use cross-catch attack. Second, by cross-catch attack, we can transform the unknown vulnerability to well-known one to simplify the exploitation. Third, with help of cross-catch attack, we can build data-only exploitation techniques to defeat growing mitigations. For example, here are some widely used exploitation techniques based on the cross-catch attack. Cross-catch attack is known as an unstable technique because it involves many steps, and each of them may introduce some uncertainty. So we start to think, are there some methods to make the entire process less unstable? Or in other words, more efficient? Actually, this is the most important reason why I want to delve into cross-catch attacks and started this research. Now let's see the common workflow of cross-catch attack. Before that, we need to know slab allocator a little bit. Here is a brief view for slab, which we allocate objects from. A slab could consist of multiple pages, and there are objects per slab objects in a slab. For a keymap catch, both objects per slab and the order of pages are exported through sysfs. Here is a view of keymap catch. There are per CPU slabs for every CPU for accelerating allocation. We need to pay attention to the partial list, which may contain many slabs. The per CPU partial list is really important part which we need to manipulate during cross-catch. As for the partial list, there is a deterministic method to put a slab into it. The first step is to create a full slab, and then pin the task on target CPU, for example, CPU 0. After that, by releasing any object on this full slab, we can put this slab into the partial list of CPU 0. This method is really useful for increasing the length of partial list. The partial list also has a flashing feature. Although it can contain many slabs, there is a maximum number of slabs it can hold, known as CPU partial, which is also exported through sysfs. Once the number of slabs in partial list exceeds the limit set by CPU partial, flashing for partial list occurs. A slab with some in-use objects are moved to slabs per node partial list, and the slabs that are empty are freed back to page allocator. After knowing the common knowledge, let's see the common workflow of cross-cache attack. Step 1, pin our task to a single CPU, for example, CPU 0. Step 2, perform defragmentation to drain partially free slabs of all their free objects. Step 3, allocate about objects per slab times CPU partial plus 1 objects for later use. Step 4, allocate objects per slab minus 1 objects as pre-alloc objects. Step 5, allocate the victim object. Step 6, trigger the vulnerability to release the victim object. And step 7, allocate objects per slab plus 1 objects as post-alloc objects. After this, we can make the victim slab a full slab. And in step 8, release all the pre-alloc and post-alloc objects. This step would put the victim slab into partial list and also make sure the victim slab become empty. Step 9, free 1 object per slab from the allocation made in step 3. Let's see this process more carefully. If we release the CPU partial minus 1 objects, CPU partial minus 1 slabs will be put into the partial list. The flashing for partial list won't happen yet. And if we release 1 more object, the flashing for per CPU partial list would be triggered, and the empty victim slab will be reclaimed to page allocator. Since the victim slab has been reclaimed, we need to heap spray object B to occupy the victim slab in step 10. In this step, victim object A gets reallocated as object B. Finally, in step 11, we can construct primitives for privilege escalation. After knowing the common workflow of cross-cache attack, let's see the 2 challenges in it. The first challenge is how to discard the victim slab onto a constrained allocation primitive. And the second challenge is how to make high-order slab reuse the low-order slab deterministically. Let's see the first one. Normally, we need to trigger the flashing for partial list to discard the victim slab. This requires not only the ability to allocate a large number of objects, but also the ability to keep them unreleased for a while. However, these 2 conditions can hardly meet sometimes. As for the ability to allocate a large number of objects, there are some mitigations like random key-malloc caches, auto slab that prevent us from finding suitable allocation primitives. As for the ability to keep the large number of objects unreleased for a while, there are some temporary kernel objects which get allocated and then released very quickly. So we can't keep such objects unreleased for a long time. The second challenge is how to make high-order slab reuse the low-order slab deterministically. Usually, if we are going to cross-cache from a bigger slab to a smaller slab, we only need to discard the bigger slab and try to heap spray many smaller slabs to reuse the released bigger slab. In theory, the reusing would succeed if we heap spray enough smaller slabs. But what if we cross-cache from a smaller slab to a bigger one? Simply allocating a larger number of objects B doesn't work. Instead, we need to get low-order pages of smaller slabs compacted into the high-order pages of bigger slab. And this requires heap shaping. Now let's dive into the main point of this talk. advancing towards a more effective cross-cache attack. And in this part, I will try to solve these two challenges. First of all, let's take a look at this vulnerability, which we will use to explain the technique details. This vulnerability is a NPU issue found by my colleague Ye Zhang, and it affects Qualcomm 4.14 kernel. This issue could lead to an UAF or double free. For more details, please refer our presentation at Black Hat Europe last year. With this issue, we can get an arbitrary key-mem cache-free primitive. To use this primitive, we must prepare the content of a victim object carefully. So this requires us to perform cross-cache attack. For this issue, the victim object is NPU network command object, which is allocated from a dedicated key-mem cache. Some basic information about this dedicated key-mem cache is exported through sysfs. For example, we can know that the order of its slab is 0, the object size is 104 bytes. There are 39 objects in one slab, and the CPU partial is 30. We can also know how many slabs in per CPU partial list for each CPU. It turns out that this dedicated key-mem cache doesn't have much slabs on partial list, and it's an inactive key-mem cache. This means it can be manipulated easily and not much noise getting involved. And here is my exploit plan for the issue. First, to trigger the issue to get the victim object, and then using cross-cache attack to let file array occupy the released victim object. After that, make use of arbitrary key-free primitive to trigger a file UAF. For this file UAF, we use DirtyPagetable to exploit it and get root. This whole exploitation is data only. However, we rely on cross-cache so heavily, which requires us to perform cross-cache attack stably to get a reliable exploit. So let's see our exploit step by step. First, trigger the issue and then start the cross-cache attack. We choose kmalloc 8k to allocate file array from. So this cross-cache attack would cross from the dedicated key-mem cache to kmalloc 8k. The slab size of dedicated key-mem cache is order 0, while the slab size of kmalloc 8k is order 3. This cross-cache just contains two challenges we need to solve. Let's see the first one, how to discard the victim's order 0 slab under a constrained allocation primitive. The NPU network command object is a temporary kernel object that it quickly allocated and released. We can trigger the allocation and releasing of this object by these NPU IO control commands. This is a really constrained allocation primitive because we can't allocate a large number of NPU network command objects and keep them unreleased for a while. Well, we found another kernel object sharing the same key-mem cache because of slab merging, but it requires system privilege to access the corresponding driver, so we can't discard the victim slab with the old method from OnTrust app. Our plan for solving the first challenge is to discard the empty slab in a race way. First, let's see a really interesting slab move primitive, which can move the CPU slab from one CPU to another CPU's partial list. For example, if we want to move CPU slab from CPU 1 to CPU 0, we need to pin our task on CPU 1 first, and then make CPU slab of CPU 1 full by allocating objects per slab objects. And then pin our task to CPU 0. After that, release all the objects allocated in step 2 step move just happens. With this primitive, we can put one more slab into the partial list of target CPU by allocating objects per slab objects at most. By repeating this slab move primitive, we can put controllable number of slabs into partial list of target CPU. By this new way of putting slabs into partial list, we can remove the step 3 in common workflow of cross-catch attack and replace the step 9 with repeating slab move primitive. Now we only need objects per slab objects to finish discarding of victim slab by repeating slab move primitive. However, it's not good enough for this issue because we can only allocate one NPU network command object and hold it for a very short time. So we have to try harder. Let's see such a risk scenario. There are n tasks. N is bigger than objects per slab. All of these tasks are pinning to CPU 1, and each of them keeps on allocating and releasing NPU network command object by calling corresponding NPU IO control. There will come a time when at least objects per slab tasks have finished the allocation of objects and still wait for their release. Since there are objects per slab allocations happening at the same time, they must lead to a full slab getting created on CPU 1. So if we just switch any of these tasks to CPU 0, a release will happen on CPU 0. This triggers slab move primitive. So as a result, this full slab would be moved from CPU 1 to the partial list of CPU 0. And we call this whole process a RISC-style slab move primitive. And here is the actual model for RISC-style slab move primitive. As we can see, there are n tasks repeat allocation and releasing on CPU 0. And another single task is used for constantly switch some of these tasks to CPU 0. With this model, we can manage to put some slabs into the partial list of CPU 0. By adjusting the number of RISC tasks, the number of tasks being switched, and the RISC time, we can move a relatively stable number of slabs into the partial list of CPU 0. So finally, with this RISC-style slab move primitive, we can add enough slabs into partial list and then succeed in discarding the empty slab with a really constrained allocation. With the new method for discarding the victim slab, we have a new optimized workflow for the cross-catch attack for this issue. The step 1 perform defragmentation with the RISC-style slab move primitive to create a new slab. The step 2 allocate the victim object. Step 3 trigger the vulnerability to release the victim object. And step 4 move the victim slab to the partial list of CPU 1. Don't trigger the flashing of partial list of CPU 1 yet. Step 5, move the victim slab from the partial list of CPU 1 to CPU 0. Trigger the flashing of the partial list of CPU 0. Step 6, heaps file arrays to occupy the victim slab. Now we have solved the first challenge. Let's see the second one, which is how to make order 3 slab reuse the order 0 slab deterministically. First of all, let's get some pre-knowledge of page allocator. Here is a simplified view of page allocator for Android devices with a single PG data and single zone. As you can see, zone normal has several different migration types of free area. In the free area, there are many different orders of pages, especially the per CPU structure PCP list is created to accelerate the allocation and releasing of order 0 pages. Normally, kernel space would allocate pages from unmovable free area by API alloc pages, while user space would allocate pages from movable free area by mmap. Some information of page allocator is exported to user space through procfs. For example, by reading the file page type info, we can get detailed information about the number of pages in the free area. However, this page type info file is unreadable by untrusted apps. By reading the file zone info, we can know watermarks of each zone and even the number of pages on each PCP list. As you can see here, we can know the high watermarks of a zone, the current number of order 0 pages in PCP list, and the maximum number of order 0 pages that can be cached in PCP list, and the specific number of order 0 pages for PCP shrink or bulk per operations. As for PCP list, there are some characteristics to note. First, the allocation and the releasing of order 0 pages always use PCP list first, and it's designed in a stack-like manner. Second, PCP list would flush the pages that add tail if there are too many pages in it. And there is another important feature we need to note. Page allocator tends to merge low-order pages to high-order pages when low-order pages are reclaimed into free area. Now that we have some basic knowledge about the page allocator, let's start to see how to solve challenge 2 step by step. The step 1, pin our task on CPU 0. Step 2, allocate many order 0 pages for triggering the flushing of PCP list later. We choose to use pipe to do the allocation. Step 3, allocate a few hundreds of physically continuous order 0 pages from unmovable free area, just like this. Well, we still use pipe to allocate these order 0 pages. And here are some details for how to allocate in order 0 pages with pipe. In step 4, we create order 0 page holes by releasing 1 order 0 page for every 8 order 0 pages. After step 4, the PCP list of CPU 0 would be like this. As you can see, there are many order 0 page holes in PCP list. In step 5, we trigger the step 1 in the new optimized workflow of cross-catch attack. As you can see here, this empty slab would come from the order 0 page holes that we have just created. After the step 5, the memory area would be like this. One of the page hole has been reused as the new slab, which is also the victim slab. In step 6, we occupy all the other order 0 page holes. This time we choose ion to do the page allocation. And the memory area would be like this. No more page holes left in the memory area. In step 7, we need to finish the step 2 to step 5 of new optimized workflow of cross-catch to discard the victim slab. As you can see that the page of victim slab has been reclaimed to page allocator. In step 8, we release all the pages allocated in step 3, except those pages has been reoccupied by ion. After this, there must be one and only one order 3 pages here. And the released victim slab must be in it. In step 9, release all the pages created in step 2 to force the flushing of PCP list. After this, because victim slab and other order 0 pages are reclaimed into free area, page merging will happen because deterministic page merging. Since the order 0 page of victim slab has been merged into our order 3 page, we can heap spray lots of file arrays to occupy these order 3 pages and finish the cross-catch. In actual practice, the success rate of the entire exploitation largely depends on the step 3. And there is a really important problem we haven't solved: how to allocate hundreds of physically continuous order 0 pages from unmovable free area. Luckily, I found a new technique with which we can detect the status of the page allocator in a side channel way. Let's see a really interesting pattern of page allocator. If we keep allocating order 0 pages with key swap D reclaim flag enabled from the unmovable free area, the page allocator would go through several states. The first state, the order 0 page would be allocated directly from PCP list. And in state 2, because the PCP list has becomes empty, the unmovable free area would be used to allocate the pages. And if we continue the allocation, the page allocator would enter state 3. The unmovable free area would become empty, and other migration type free areas will be used for allocation according to the fallback list. We need to note that when the fallback happens, QSwapD would be woken up for reclaiming pages if the number of free pages is below the high watermark. And if other migration type free areas become empty, the page allocator would enter slow path for allocation. This is a state 4, and there are several actions taken by kernel to reclaim free pages, including waking up key swap D to reclaim pages and direct reclaim and so on. Normally, kernel would reclaim pages from several fixed locations, which includes 4 LRU list and shrinker list. And luckily, the number of pages in each of these lists are all exported by the file proc meminfo. And the meminfo file is accessible from untrust apps. So as a result, if we observe values in the proc meminfo while keeping on allocating all the 0 pages, we will see these 5 values get reduced frequently at a very time point. If this happens, the page allocator might be in state 3 or state 4, which means our movable free area is almost empty. And here is a test result on a device with kernel 4.14. As you can see, we can detect the status of page allocator and know the exact time when unmovable free area is almost empty. So here is the strategy for allocating a few hundreds of physically continuous order 0 pages from unmovable free area. Step 1, reserve a dozen of high order pages with ion. Step 2, create and detect the empty state of unmovable free area with the technique we mentioned. Step 3, release the high order pages reserved in step 1. And step 4, allocate some order 0 pages to reduce noise. Step 5, allocate a few hundreds of physically continuous order 0 pages from a mobile free area. Under this condition, order 0 pages come from the splitting of high order pages. This guarantees these order 0 pages will be physically continuous. So we just solved the second challenge. After we succeed in the first stage cross-catch, we will get a file UEF. It's time to exploit file UEF with the dirty page table. And this time we use the old method to discard the victim file P slab and occupy the released victim file P slab with the user page table by heaping spraying many user page tables. To improve the success rate of a cross-catch, we use the mentioned method to make the unmovable free area become almost empty in the first step. And as last year, we have demonstrated how to root several Android devices with dirty page table, but we haven't demonstrated how to root Samsung device with dirty page table yet. So this time, let's do this. For Samsung device, it has some mitigations such as physical KASLR, read-only kernel text, which prevent us from constructing physical AARW with dirty page table. But we still can choose to corrupt kernel object to construct AARW. Here we can easily get this seen by dirty page table. As you can see, we control a valid PTE, which corresponding to a physical page owned by ION. This physical page can be accessed with the user virtual address from user space. And we choose to corrupt pipe buffer to construct AARW. To finish that, we need to make the page of pipe buffer follow the page owned by ION. This can be done by using mentioned technique for allocating physically continuous order 0 pages. And then we add OX 1000 to this victim PTE. By doing so, we can totally control the pipe buffer. And it will be easy to use pipe primitive to construct AARW. And to bypass SLinux in Samsung device, we choose to attack the global data used in security compute AV function, which is used to compute the AVD. And finally, we won the game of cross-catch. We removed the requirement for system privilege and improved the success rate of exploit to about 65%. As for mitigating cross-catch attacks, there are actually many techniques available. The Slab virtual is a really powerful one, which basically killed the game. And here is the summary. In this talk, I solved 2 challenges in cross-catch attack and adapt dirty page table to Samsung device. And thanks Ye Zhang and teacher Jing for helping me with my slides and the talk. And thank you all for attending my presentation. So is there some questions? Okay, thank you all.